name's Bob Hawkins, and I thought I'd give a little introduction to Bill because he's a modest guy and most of you won't know much about him. Bill is a veteran pilot. He has over 18,000 hours. He grew up in the Sault Ste. Marie area, joined the RCAF in 1951 when I was 2. And he served as a pilot in many capacities, 426 Transport Squadron in Trenton in the 1960s. He logged over 2,400 hours in the Canadair DC-4 North Star aircraft and actually flew here the North Star that's in the Chasm collection, as I understand. Eventually, Bill joined the RCAF's 412 VIP Squadron, based in Ottawa, where he transported royalty, heads of state, and other dignitaries, as well as politicians and high-ranking military officers. Bill's portfolio includes Prince Philip, Prince Charles, Princess Anne, Shah of Iran, and many others. These flights were made in the RCAF's Cosmopolitan aircraft. That's another version of the Convair 580. While he was still with the RCAF, Bill was seconded to NRC in 1972, primarily to fly on their ex-military North Star research airplane, fitted with a single-tail magnetometer that was replaced a few years later by a Convair 580. Bill can tell you the story of getting that at another time, but it's an interesting one. In 1975, Bill retired from the RCAF and continued with NRC as a civilian research pilot, as the supervisor of flight operation and training until his retirement in 1990. When Environment Canada acquired the airplane we're going to talk about in 1996, Bill continued to pilot this aircraft on an ad hoc basis until its last research flight in December 2009. I think there's no better person to tell you about this aircraft than Bill Chevrier.
Well, thank you, Bob, for your kind words. And good morning, ladies and gentlemen. I'll be telling you briefly about the Convair registration marks Aviation 1 is Charlie, Golf Romeo Sierra Charlie. And as mentioned, it's a twin-engine turboprop aircraft that the Government of Canada has used as a remote sensing research aircraft from June 1977 to 2009. In 1977, the aircraft was converted to a research configuration where all the passenger seats were removed and replaced with research equipment. And that included a large circular cavity in the mid-belly of the aircraft that is covered by an exterior radome. A few science research stations with their crew, member seats, and other stuff. The two scientists that will be speaking after me will elaborate on the other stuff. In 2014, the aircraft went to the National Research Council for Safekeeping, and finally in 2015 was transferred here to the Aviation Museum. I believe it's in the storage hangar next door. Now for some information about the aircraft, if you're not familiar with it. The length of the aircraft is 81.5 feet with a wingspan of 105 feet. The height is 29 feet and the wing area is 920 square feet. The aircraft is powered by two Allison turbojet engines that can produce 3,750 horsepower each. They're the same type of engines that are in the Hercules, the C-130. The propellers are the Pac Aero Aerospace four-bladed auto-feathering, full reversing types. The aircraft's previous basic weight with its passenger seats was 32,500 pounds, whereas as a renovated research aircraft, it is now 44,000 pounds. Finally, here's some of the aircraft's operating information. The fuel type used, of course, is Jet A or A1 and even Jet JP4. The fuel capacity is 2,900 US gallons, or 19,720 pounds. I've never had to use a full fuel tank of fuel. Maximum takeoff weight is 58,140 pounds. Max cruise is 297 knots, and that's at 20,000 feet, and the service seating is 25,000 feet. The range with 5,000 pound payload is 1,970 nautical miles. Now they call this a medium range aircraft. I don't know the difference between medium range and long range, but it's up there between them, I believe. If you put a maximum fuel load on, it goes up to 2,577 nautical miles. The sideline, if I flew this aircraft once non-stop from St. John's, Newfoundland to Shannon, so it's reasonable range. That's my allotted time talk. So if you have any questions, I believe it's going to happen after the other two people talk. Okay. Thank you very much.
Okay, thank you. Bill was my captain for many years, and I always enjoyed flying with him. And since the aircraft came here, we've got to know each other a lot better as he's been helping me understand a lot of things that I never understood before. I sat in the jump seat as a research scientist between the two pilots, thinking I might learn something about flying an airplane, and I always gave up because there were those million gauges, those 1,000 switches, and things that only pilots knew. But it was a thrill to be able to do that. I started at the Canada Centre for Remote Sensing in 1978 and worked with the aircraft until our department, which became Natural Resources Canada, gave it up in 1995. And then later, Environment Canada took it over, and that's the time that I knew Bill best because he flew with the aircraft most of that time. So I'm going to try and give you a little bit of history of the aircraft. It's shown there in the NRC hangar. It looks bigger there than when it sits outside with no context. The next slide, please. Maybe I can do this myself here. Okay. This is a little chart of the history. You can see that there were many owners. It was manufactured in 1953 by the Consolidated Volta Aircraft. That later became, I think, General Dynamics. This company had a big history of making bombers and aircraft during the Second World War. It flew first as a commercial airliner. I think they were called airliners because we had ocean liners, and these were airplanes that took people in the air, so they're called airliners. And it spent about 5 years with United and put on, together with Johnson & Johnson, a private company that bought it, about 20,000 hours. During the time that it was with Johnson & Johnson, it was converted from a passenger airliner to a kind of an executive transport. And I'll show some pictures of that. It was also converted from a Convair 340 into a Convair 580, which Bill described to you, with these larger engines, a bigger tail section, and other kinds of changes that made it into a much more robust and versatile aircraft. It spent 3 years with Great Lakes Pulp and Paper under the call letter CFPGY. It spent 1 year or so with Save a Stop in the U.S., gathered another 800 hours of flying, and then spent 12 years with the Canada Centre for Remote Sensing. This was a new organization in the Government of Canada. It was founded by our first Director General, Larry Morley, who was inducted into the Science Hall of Fame here a few years ago. Larry had worked on radar during the Second World War, and there were many stories about him convincing ships, pilots, and so on, captains, that radar could actually do something interesting. And he believed that Canada needed radar, and I'll talk a little bit more about that. In 1996, it was transferred to Environment Canada, who had a program in emergency science. And they had two of our previous aircraft, the DC-3, which eventually went to the War Museum in Lancaster, about the same time as this aircraft came here. And it spent a year with the NRC. They had originally intended to scavenge it for parts because they have a research Convair as well. But we were lucky enough to keep it intact enough so that it could be flown here and become part of this collection in June 2015. The aircraft has a total of 27,000 hours on it. That's not much for an aircraft that old. This chart here shows the same information in a little bit different form. You can see at the top its lifetime as a passenger aircraft, then as an executive transport, and then for almost 35 years as a research and development aircraft for Canada. And I can't emphasize that how important it was to have a dedicated aircraft for this work. We worked with many other countries. They had small aircraft, sometimes bigger ones, but they never had dedicated aircraft. This aircraft was dedicated for research, and it became both a research facility and an operational facility, so that you could have this aircraft do work on consignment, and it was done that through private companies like Intera and Birchow later on in its career. So at the bottom you can see that by far the most hours were done with United and Johnson & Johnson. And as a research facility, we put almost 6,000 hours at the Canada Centre for Remote Sensing on it. That's not many hours, but it was all dedicated to this, a huge luxury for the Government of Canada. This is what the airplane looked like when it was with United. And I believe this is our aircraft. We don't know that for sure, but it has the right call letters, and it has some insignia on it. So we believe this is the only picture I have of it as it was an airliner in 1958 with United Airlines. It flew out of Spokane, Washington. When it went to Johnson & Johnson, This picture was captured in Gatwick Airport. I contacted the people at the Gatwick Historical Society, and they graciously gave me permission to use their photograph of it. You can see it's got 3 props on it. Later on, you'll see that's changed to a 4 prop. If you look carefully, you'll be able to see that the tail structure looks a little smaller here than it does in later pictures. When it was with Great Lakes Pulp and Paper, this picture was taken in 1970. It says Timmins on it, but that's Timmins Airline in Toronto. You can see the larger engines on it, the 4 props, the larger tail, and a different paint style. The aircraft looked largely like this when we got it in 1974. Why does Canada need radar? I thought I'd show you a series of a few slides to demonstrate this. At the bottom are a number of Canadian cities which are familiar to you, from St. John's to Winnipeg. And what this is showing you is how many hours of cloudless day we have in those cities. And about half of the time, we're covered with cloud. Radar sees through clouds. That's one good reason for investing in radar. As you know, we have day and night here, but we have in our northern regions a lot more night than day during the winter. How are you going to cover and understand that stuff with an optical instrument? You need radar to do that. We have a big country. On the right is a satellite picture showing the illumination at night in mostly the United States and Central America. You can see that we don't have the lights on too much in Canada. Most of it's not very well populated. We have 9 million square kilometers of area to understand and survey. We have a huge coastline, and we have low population. We need remote sensing to do that, and radar is one of the big tools that will help us with that. This is the configuration of the Convair as a research aircraft in its final stages. Bill referred to the main radome underneath. That hole was cut by Initech Aviation in Montreal. The aircraft spent about 2 years getting ready for the instruments down there. It then went to Northwest Industries in Edmonton for further fitting for racks and so on. Above it is the INSAR antenna, and we'll come back to that later, but basically the main part of the aircraft is filled with racks of electronics. Most of them are from a company called MDA, which you will know from the Canada Arm, from a RadarSat 2, a RadarSat 1, and we were part of investing in that company, getting it going in the remote sensing sector, and I think they are proud as a company to have been part of this story as we are to have had them. Other companies that were involved were Canadian Astronautics, local companies like Newson Engineering in Perth, and almost all of the equipment on board is Canadian designed and built, and it's a success story for Canada. This is the antenna. I showed actually 2 antennas. At one stage we had 3 frequency bands, L band, C band, and X band. For those that think about wavelength, L band is meter-sized waves. C band about 5 centimeters, and X band about 1 centimeter. At the top is the X band antenna, and at the bottom is the C band. They were horn. These were made by a company called ComDev. They reside in Cambridge, Ontario, and have built all kinds of high-tech equipment for space and for us. The engineer who worked on this antenna was a guy named Tony Rabb. There are actually 4 antennas here. There's 2 polarizations for each of these 2 horns, and it is a mechanical marvel as well. The antenna was steered in elevation, so if the airplane is going in this direction, we would normally look out to the right or to the left. So there's a large beam radiating a swath to the side of the airplane, and it had a narrow beam in azimuth, and I'll explain that a little bit. But this antenna, we would normally steer it in elevation so that when the airplane rolled, the antenna stayed still. And we also steered it in azimuth to be what we called a zero Doppler antenna to help us with the processing. And later on we added a pitch axis in the aircraft to keep it steady. So this is 3-dimensionally stabilized in flight. This graphic here is to help you understand how you form imagery from radars. It's a side-looking radar. When we started out in this business, they were known as SLARs, side-looking airborne radars. As you can see in the picture, there's a broad beam across the swath and a narrow beam in azimuth along the track. And so if you imagine at the far right there, you send out a pulse, it comes down to the ground, and that pulse strikes a series of pixels across the swath, and then you pick up the intensity of that radiation coming back, and you can see it produces a band of varying intensities for each pulse that goes out, and then you move along and you send another pulse, and you do the same thing, and from that work you generate a radar image as you go along. What I want you to notice about this is that the beam spreads in azimuth as you go here. So it's narrow at this point, and then as you go across the swath, this distance might be 18, 20 kilometers here that we're measuring. So the beam is fairly narrow here because it's a shorter radius and a longer radius here. So the resolution of this thing in range varies. That changes when you go to synthetic aperture radar. And the next slide illustrates that a little better. So in this case, this footprint that you have here instantaneously gets divided up into smaller resolution cells by processing. It takes for our aircraft about 9 or 10 seconds for the beam to go by a point. And you collect all of that data in amplitude and phase as you go by it, and then you process it in various ways. Nowadays it's all done digitally. Originally it was done with this laser beams and series of fancy conical lenses and holographs. But the net result out of that is that this wider footprint gets made into smaller ones which are independent of range, and equal to half of the length of the radar antenna in azimuth. So that antenna, which we looked at here, which was maybe 2 meters long or so, gives us a resolution on the order of half a meter when we're finished this, independent of range. So that's the C-band antenna shown there. Just a little bit about electromagnetic waves. As you know, they have an electric field vector shown in red here, which is oscillating up and down, and an attendant magnetic field. And these things feed on one one another and generate each other. The height, whoops, the height of this is this amplitude gives us the intensity of the radar. So the more power that you put down on a target, the more you get back. There are two other aspects about this which I want to point out to you. One is the wavelength, and the second is the phase. So if you move this peak along a little bit, its phase has changed, and Dr. Gray will talk a little bit about that in the context of interferometry. The fourth thing I want to say about this is polarization. This electric field is here shown going up and down. That would be vertical polarization. If you rotate that 390 degrees, that's horizontal polarization. And you can have any combination. You can even have circular polarization. So this radar that we worked with exploited these four properties of electromagnetic waves. Its amplitude gives us the intensity of the scene. The phase gives us information about the target itself. And polarization is another property that comes in here. This beam goes down and scatters off. It might scatter off the tables here or somebody's bald head or whatever in here. When it comes back with varying intensity, polarization, and phase. And those are called the scattering properties of the things on the ground. And when you fly a radar, the idea is to understand what's on the ground, and you do that by studying the properties of the scattering that comes from it. We had three frequencies initially when we got the radar. We have multiple polarization. Remember I said the antennas were actually four antennas, one for H polarization, one for vertical polarization each. And we could simultaneously measure these things. And we could also measure phase. So when you measure just polarization, that's called multipolarization. When you measure phase and use it in a differential way, that's called interferometry. And when you use polarization and phase of the scattering, that's called polarimetry. And those are all advanced radar techniques which we try to exploit and learn about. Our task as researchers at Natural Resources Canada and Environment was to understand how to best use a radar like this, how to design it, how to measure with it, and how to exploit it to characterize natural resources. So in the group that I worked with, we had the advantage of an aircraft, people that worked on the aircraft, people that worked on the radar, people that worked on application, and people that knew the technology, all in one little group of 20 or 30 people. And it was an exciting time to be part of that story. I just show you this to give you an idea of what a radar image looks like. This is a multipolarization image on the left-hand side of the Columbia River Valley in BC on the bottom left. You can see the mountains on the right and a valley on the left of it here. At the right end, whoops, I can't do this. At the right hand side is a Landsat optical image, and what I wanted to show you here is that, well, for instance, this little field here, it's a clear-cut area. In this image, it's dark on a bright background of a forest background, and on the right-hand side, you can see the clear-cut area, same one, in bright with a dark forest. Radar sees the world differently, and our task was to understand how it sees that and try to exploit that in a way that could be used for Canada's needs. This is a picture of one of the recording systems. There's a kind of a big mother cassette. That's actually my daughter there about 25 years ago when we first put this in here. These racks aren't in the aircraft now, but they somehow got lost, and I've had some volunteers refabricate these, and we hope that this equipment will get reinstalled soon. We put everything on tape in those days. Tape was the only media that had the capacity and bandwidth to carry this early on. Nowadays, you would put that on disc, but that was what we used and what we had. This is one of the MDA installations here. This is a, excuse me, I just can't help myself. This is what we call the real-time recorder paper. It produced a waterfall of dry silver initially, and as we went along, you would see an image unfold as we went. There was always that delay because you had to wait until you got that 9 seconds past the far edge of the beam to go by. Then it had to go through a processor and it would scroll out. So you would be looking at past tense data when you did that, when we called it real time. There's communication gear here, another recorder, and other kinds of stuff in that picture. This rack also mostly, well, the stuff at the top was built by Cal. In the original contract, which came, this is the second generation radar, about 1986, there were two companies involved. MDA was prime and Cal was a subcontractor to them. Cal built all the RF equipment and MDA built all the digital control equipment. C-GRSC built the mechanical stuff, and so that is, this is the antenna, 3-axis control for the antenna. This is the power for the RF section, and this is the control for the radar itself. We had basically two operators who run. One ran this station and one ran the recording system. This is an area which we call the swimming pool. It was just in front of that radome that Bill pointed out. And in it, you can see several things. One is the RF transmitter. And right here is the INS. We eventually used the Lytton 92 INS. That measured our position, our velocity, all our accelerations and attitudes. And those things fed into the radar control system. They also fed into the autopilot. So this was an integrated system. I can't emphasize that much. The radar was built for the aircraft, and the aircraft was bought for the radar. When the museum looked at getting this system, I remember making inquiries about it, and the first response was, well, we don't have room. We can't get that aircraft. And so the next response was, well, maybe somebody at Science and Tech might be interested in the radar. And so Dave Pantalone came over and looked at it, and it didn't take long before people recognized that the radar might be a pile of junk that people would look at in the corner of the museum once in a while. But it's the system integrated together as a radar laboratory, which is the story that we experienced and needed to tell. And Stephen Quick came over, and other people from the museum came over, and they easily grasped this concept and understood that this wasn't just another aircraft or another radar. This was a system that needed to be seen as an integrated system, and the story told that way. It didn't take long before other countries recognized Canada's leadership here. In 1983, the Japanese contracted us to go to Japan be centered in Sendai, which you remember was part of the large tsunami a few years ago. To get the aircraft there was a challenge. Large as the range is for it, you can never fill it up with gas because even though it might hold 19,000 pounds of fuel, it has so much radar equipment in it, you can never get that much fuel in it. So the way around that was to ship as much as you could and then put on as much gas as you could. And this is the route that the pilots took at that time from Ottawa off to Anchorage, across the Aleutian, down to Midway, Wake Island. I remember the pilots told me that when they got to Wake Island, they were running on fuels. There was a cloud over the island. They didn't see it. And then they looked back and said, yeah, that's it. And they quickly got down. But that was a big trip. The Pacific is huge. But that's one trip that happened. I remember taking my father through our lab, and he said to me, well, yeah, it's nice the aircraft can go to Japan. We can learn a lot from them. And I said, no, that's not what's happening here. We're leading. Canada is leading in radar, and we're showing the rest of the world how it's done. This is another aspect of work that was done with this radar. It was small, but it was significant. Right there, you'll see our current Minister of Transport, Mark Arnault. There's Roberta Bondar, and there are other astronauts in this picture. Bill flew these astronauts in zero weightness conditions with NRC, but we took them out. Well, I say we, but in this case, this was a professor of geology from Carleton University who took the astronauts out to see what the world actually looks like from on high and tell them a little bit about synthetic aperture radar. Mark Arnault flew on one of the shuttles, and I remember Lawrence being involved in an experiment over Labrador with Mark later on. So other people knew about this system. This is several of our pilots. This is Andre Gignac, Alfie McDonald, Bill Baer, and a series of other people in this picture. So that's 1995. This is another trip that took place in 1992. I don't want you to get the idea that all we did was exotic trips. These were special trips. People remember them with a great deal of enthusiasm, but by far and large, most of the flying of the airplane happened in Canada. A great deal of it went to the Arctic, and Lawrence, I think, will tell you about some of the early ice research that we did at that time. But these were trips which were significant. This was a trip sponsored by the European Space Agency in 1992. They took the aircraft to South America. At that time, they were getting ready for ERS-2 and ERS-1, and they needed basic data on how radar sees the Amazon in particular. This area, this area here in Colombia and in Brazil is heavily rainforested, and when satellites got radar in space, these were targets which were used for calibration of those radar, and we were part of that story. There are other ones that I could tell, but I'm not going to take all your time. These are two of our pilots. Here's this Jim Spicer and Brian Healy, who flew with Convair probably longer than anyone else, and was the manager for Environment Canada. Well, it spent 15 years there. This is one of the last things that the Convair did. We worked with many other departments in Canada. The aircraft belonged for a lot of its life to Natural Resources Canada, and later Environment Canada, but we flew for DND, we flew for Environment, we flew for Agriculture, and in this case they were doing an experiment for DND to develop their Aurora radar, and to do that we got a different radome on the rear. There's a spinning antenna in that, and that work happened for a couple of years, and that was probably the last mission that the aircraft did. Its last flight was, I think, in December 2009, and this was the configuration of the aircraft at that time. I wanted to just say a little bit about three guys here which were instrumental in getting the aircraft here. At the top is Ian Boakey, beside him is Johnny Mintha, and down here is, I lost his name, excuse me. These are AMEs at Transport Canada. Well, why was Transport Canada involved in this? Well, they weren't. They volunteered. These guys worked from about 6:30 in the morning till 3 in the afternoon. And when they found this aircraft was going to come to the museum, they volunteered to help get it ready to come. When it was in its last few years, it was in storage in the alert hangar at Uplands Airport. To get it in that hangar, you had to take the tail off. The hangar was designed to spoil voodoos and stuff during the Cold War, and they had huge hangar doors, but it wasn't high enough to let this huge tail into the Convair, so that had to come off. And one of the things that Johnny and excuse me, I can't remember the guy's name, worked on was reinstalling the rudder and the tail section before it went on. They ran the engines up. They did everything that was necessary, and then they delivered it first over to the Transport Canada hangar, and then to NRC where it stayed for a long time. But I can't say enough for the work that these guys had, the skill and the dedication they gave to getting this aircraft ready to come here. When it arrived, we had a little VIP picture here, and I wanted to just say a little bit about the people in this picture. It's very rare that you can get more than one government department to cooperate, and in this case we had to get the museum people, Environment Canada people, and NRC together and working in the same page, in the same framework. And the guy who did most of the work from the perspective of Environment Canada is Dr. Carl Brown here. Carl was the guy in charge of the Environment Canada aircraft and the Agency of Science at that stage. And he looked the other way a great deal to allow people like John and Ian to work on this day and night to get it ready. You can see Bill supervising the whole situation here. This is Mike Kirby, who worked with one of the private companies that leased this aircraft from time to time. Theo Van Westrop, probably the longest engineer that worked with the aircraft. He's now at NRC and is the chief of maintenance on their Convair. This is the then Director General, Stephen Quick, who I talked about earlier. The two pilots from NRC, this is Paul Brown, Brown and Paul Kistman. Paul's the chief pilot in NRC, a position that Bill held many years ago, and the director of the NRC Flight Research Laboratory, Stephen Parkson. It was quite a job to get all these people to work together, but they did, and I think we owe a great deal of thanks to them to get the system, along with many other people, of course. This is the aircraft arriving here on June 22nd. Yeah, it was a windy day. NRC wanted a strong wind going up the runway so they could get it down. And originally we had a longer runway here, but this aircraft typically needs around 5,000 feet. They had a very strong gusty day, and they brought it down halfway down the runway, and it was very well done and an easy trip. They flew at about a couple thousand feet, with the gear down all the way, and there's a video that Glenn and I are working on from that trip that will be available eventually. When the aircraft got here, sadly, and it was parked outside, it was covered with plastic to help preserve it. There was a furnace and air conditioning system put inside, and it sat out for a year or so, roughly, and thankfully it's now inside, and we hope that it'll be more accessible. So this is the aircraft. I think this is when we went down to Swiss Air flight that crashed, Swiss 111. And we did surveillance around the Halifax area at that time. So this is Halifax. In a vision for this aircraft, it's what we heard from people this morning. We want people to know this proud story. We want you to be able to tell it as guides, and we want people to know it in years to come when we're not here to tell that story itself. So we're trying to work on a plan to help that happen, and I hope this gives you some sense of where the aircraft came from, how we used it, and I'm going to follow up here with just a little introduction to my colleague, Dr. Lawrence Gray, who will tell you a little bit more about some details of the applications that we use. So you get a sense of the science rather than the technology, which I tried to emphasize here. I knew Lawrence as a graduate student at the University of Guelph back in the 1970s, and he had come from Belfast, Ireland, done some work as a postdoc, I guess, at the University of Calgary, and then came to the University of Guelph and did light scattering. And you might ask yourself, well, by the way, I did neutron scattering. In the days when we were working on the wave that brought radar remote sensing to our department, there weren't any specialists in remote sensing. We had people that were engineers, people who had flight experience, people that Lawrence came with a light scattering experience. I came with neutron scattering. Other people were astronomers. Nowadays, there are people that actually graduate with degrees in remote sensing. But in those days, we had a hodgepodge of experts who had an uncanny thirst in doing a new kind of research and applying their skills in basic science to working on it. And Lawrence was one of those people. And I had the privilege of being first as a postdoc, and then later working as a colleague and friend of his. So I'll let Lawrence come up and tell you a little bit about the science.
Okay. The division in the Canada Centre for Remote Sensing that looked after the Convair, looked after the airborne program, was relatively small, and we had engineers, technicians, machinists, and so on. And okay, thanks, Bob. And then, of course, with the aircraft, we had sensor operators, pilots, and so on. But as well as those groups, there were a few of us who were scientists. And our role in the business was to define specifications for radars and so on, to check equipment, to liaise with scientists outside the organization. But thankfully, we also had the opportunity to design our own programs, to participate in experiments, and to demonstrate the value of the radar technology. And of course, to do this, we were often part of the crew that flew with the Convair. And the sensor operators, of course, didn't trust us to operate the sensors quite wisely. And I think, to be honest, a lot of the time we were just in the way. And I think this is why we got the title as the SOBs. And of course that stands for Scientists on Board. And perhaps I should say that I think, as Bob said, we were very lucky that it was a relatively small group and that we knew everybody. We knew the engineers, the pilots, and so on. And there was a lot of cooperation between the various groups. So very quickly, a little bit of history. The Canada Centre for Remote Sensing began in 1972. I joined in 1974, and at that time there was already an airborne program. We didn't have the Convair, but we had 2 DC-3s and a Falcon fan jet. And the Falcon fan jet came from a company that had been doing work for NASA. And there was a scatterometer. This is a calibrated radar which didn't create an image, but provided quantitative measure of backscatter. And it really wasn't appropriate for the Falcon at all. This is a sensor that you want to fly low and slowly. So it was perfect for the DC-3. So that sensor was put onto the DC-3, and that was what I got involved with initially. Again, as Bob said, from a Canadian point of view, it was obvious that we would like to develop the whole business of radar technology and radar imaging. And on the left, we also have the list of the various radar technologies that we had. The Ku-band scatterometer, this is the one that was on the DC-3. Eventually, we put it also on the Convair. We had an arrangement with the Environmental Research Institute of Michigan. They had developed synthetic aperture technology, but they had a terrible aircraft. So that, we borrowed their radar for a few years in the 70s. Then we added a C-band scatterometer to the Convair, and then finally in the mid-80s we had our own Canadian-developed synthetic aperture radar system, as Bob described. So I'm going to give you a very quick introduction to some of the areas that we were involved with in the division in CCRS. But this is only a small part of the science that was done with the Convair. And again, we're going to begin with describing some of the work that we did in the ice reconnaissance area. Now, at that time in the mid-70s, the agency in Canada that was responsible for providing information, ice maps and so on, was part of Environment, the ice services, and they had reports from ships, and they also used some aircraft observations. And the big one they had was, I think, a Lockheed Electra. They had a bubble in the side of that Electra, and they had a guy drawing ice charts. So he had to see the ice, he had to interpret it, and obviously you can't see that far. So again, this was an area that I thought at the time that really radar had to be a better tool to create ice charts. But the ice services were quite conservative. They wanted to know, well, what can you see in that imagery? Can you tell the different ice types? Can you provide the information in a reliable form that we can provide then to our users in the shipping that was going along the East Coast and the Arctic and so on? So beginning in 1975, we had an opportunity to participate in what was called the Arctic Ice Dynamics Joint Experiment. It's a Canadian-US experiment. It looked at a whole number of areas, but there also was a remote sensing component. So we took our DC-3 to the Arctic. DND were flying Arguses at that time, And one of the Canadian Arguses was equipped with a real aperture radar, as Bob described. And they took some imagery of the site, and also NASA participated with their Convair 990 aircraft. Now, we flew to the Arctic. We were based first in Tuktoyaktuk, and then to participate at the HX site, we flew to Point Barrow. Now, the site was a camp on the sea ice, but it was so far north of Point Barrow that there was no way we could fly there and back again. The range was too far. So we landed on the sea ice. The image on the right is us landing the DC-3 on some relatively smooth first-year ice. So the ice was maybe a couple of meters thick, and the camp is in the area. We refueled the plane, a lot of pumping to refuel the plane. Then we took off again, flew the flight lines, and went back to Point Barrow. Now, the NASA aircraft was a Convair 990, and if you don't know what a Convair 990 looks like, there it is, overflying the camp. In the foreground, you can see some of the camp that was set up at that time. I'm sure they must have used Hercules to bring in some of the equipment to set up the camp. But, I don't know, maybe the Convair came from California, I don't know. I'm not even sure what sensors they had on board, but certainly the work we did then with the scatterometer, and I'll keep the science to a minimum, but I'll show you a little bit of data that we collected from the DC-3. The DC-3 was a wonderful remote sensing aircraft. We had 4 big holds so that we could put things like mapping cameras, infrared equipment in these bays. And at the bottom, you probably can't see any of the details, but there was photography. And from the photography, from the information of the people working in the ice, we know the kind of ice types that we were flying over. And on the top, you can see the big change in backscattering between the multi-year ice here and the first year in young ice on this end of the imagery. Now, from a point of view of ice reconnaissance, you want to be able to recognize the thick, strong ice, this multi-year ice. It's survived one or more summer melt periods, so a lot of the brine has drained out of the ice. It's thicker and it's much stronger. So if you're operating a ship, even an icebreaker, you want to avoid this kind of ice. And that's the sort of thing that the ice branch wanted to be sure that we could recognize in the imagery. And we argued on the basis of the scatterometer that yes, radar should be able to do this. The trouble was the D&D Argus with their APS 94, one of the scientists at the Defense Research Establishment, Ottawa, as it was called then, sort of criticized our work, saying, no, from the APS 94D, you can't always tell the multi-year ice from the first-year ice. But the problem was they were flying relatively low altitude, looking way out to the side. And with that kind of geometry, what you see is the ridges, the things that are sticking up, the large-scale roughness. Whereas if you're using the kind of geometry that a satellite radar would use, which is the kind of geometry that we have here, these are the incidence angles, by the way, that we were using. Then you do have this nice contrast between the various ice types. And a few years later, we were able to prove that this was correct. This is now in 1979. At this stage, we had the Convair, we had the ERM XL radar on board. We flew Arctic missions, and I'm afraid you may not be able to see the imagery particularly well, but if you just look, this particular pass was done with low altitude, kind of duplicating the geometry that the military had flown with the Argus. And you see at the far range, at the sort of glancing, these small grazing angles, that's all you see. You just see the large-scale roughness, the ridging, and so on. So that I think that the kind of work that we were doing, where we were looking at the different radar parameters and showing that yes, synthetic aperture radar will be a good tool for ice reconnaissance. So this work that we did helped justify the RadarSat program. It led to when there was more Arctic exploration by the companies like Canmar and Gulf and so on, they used airborne synthetic aperture radar, commercial opera, to support their operations. And now, of course, the Canadian Ice Services, as soon as RadarSat-1 was launched, which was in 95, this is an early RadarSat-1 image of the Beaufort Sea. And again, you can see right away, these are the multi-year ice flows in the Beaufort Sea. This ice down here, the darker ice, shore-fast and first-year ice. So now, of course, the ice services depend on the RadarSat imagery to provide their ice charts and their ice information. Okay, let me talk very briefly about some of the work we did for the European Space Agency. Again, this goes back to the mid-80s, and at that time, the European Space Agency were, like Canada, looking ahead to develop remote sensing satellites. And again, like Canada, they wanted to have a system that was all-weather, day-night. So they were looking ahead at developing radar systems that would be useful in a European context. And perhaps I should say that Canada was then, and still is, an associate member of the European Space Agency. So some of your tax dollars does end up at ESA, but of course there's return for that, industrial return or one form or another. And another thing I should mention, that whenever the Convair went to Europe or internationally, your tax dollars didn't pay for it. There was always a contract involved, there was always a payback for it. So the European Space Agency paid for our participation in this ocean backscatter program. So there was 4 aircraft involved, the Convair with 2 calibrated radars, and the idea is we would operate out of an airport in Brittany and do ocean backscatter measurements on various days with different wind speeds. And there were 3 other aircraft involved as well. The German Dornier 28, and they had taken out the door here. This is actually an antenna, and after they took off, that antenna would be shoved out the door, pointed down at the ocean. And it's quite an operation. This is a Dutch plane. They nearly flew into us in one day, but happily we didn't have a mid-air collision, although it was close. And here's their antenna underneath it. And this is a French plane, and I'm sorry, maybe some of you know which plane it is. I'm not sure what it is. But I felt sorry for the French scientists because the French group had a lot of problems with that plane. So let me, okay. So the kind of thing we're leading up there is to provide the basic information on the way the backscatter varies with wind speed. As you can imagine, as the wind gets stronger and stronger, the ocean gets rougher and rougher, and you get more backscatter. But it also depends on the angle that you're looking with your radar in relation to the wind speed direction. So this is actually a satellite product done. It was, I think, a NASA NOAA satellite called QuickScat, and this is a wind field derived around the eye of a hurricane. So again, there are similar products from the operational European Space Agency satellites that are up there right now. Okay, I'd like to finish talking a little bit one of the kind of unique experiments we did at CCRS, and it's referred to as interferometry. And Bob mentioned a little bit about some of the radar aspects, but let me just repeat so that you can have a little bit better feeling for what the phase is. And here's a radar on an airborne or satellite flying along here. And here's the illuminated patch in the ground from the side-looking beam. Now, so you could think of a target passing through this beam. And of course, it's illuminated by maybe up to 1,000 pulses. And for each one of those pulses, the radar range between that target and the middle of the antenna and back again is changing. And that's what the phase measures, so that because you know what the Doppler history should be, if you use that Doppler history, you can now do what's referred to as azimuth compression, but focusing, creating a smaller pixel than you're actually illuminating. And the nice thing is when you finish that process of processing the imagery, you still have this relative range between the antenna and that scattering center. So if you think of, here's a little image here. This is a C-band image, and maybe, I don't know if you can see it, but this is our test line in Ottawa. Here's down at the bottom the Ottawa Airport. Here's the Rideau River. Here's River Road. Here's Linebank Road. This is the building that we worked in, and we had 5 concrete posts sunk into the ground, and we put 5 radar reflectors on the top of those posts. And we were flying along up here, looking this way. So the reflectors are pointing back towards the radar. Now, if I was to show you the phase image corresponding to this, it would look just like noise. But if I'm correct in that the phase represents this detailed range, then if we were to be able to fly that flight line again in exactly the same position and compare the phase from one pass to the next, it should be the same, right? So you can't, I went to the pilots and said, okay, I'd like to fly this flight line many times, maybe 8 times, but I want the plane to be within a few meters of where it was the previous time. And they kind of looked at me, and maybe this is why they call this SOBs, I'm not sure. Okay, we'll give it a try. So they did this, flew it 8 times, and it's only going to work properly if you're close, if you can repeat that track within hopefully a few meters, maybe less than 20 meters. And in fact, we got at least 3 pairs where the flight track was repeated closely enough that we were able to do these experiments. And I'm going to show you, the next one shows you again the same images at the 2 frequencies, but now the color represents the difference in phase. And you can see clearly that's not noise. There's a definite, if you like, an interference pattern there. And what I didn't know at the time, but others in NASA, in JPL, in Europe, were trying to do this kind of experiments with airborne radar. And we did it first. And you're probably thinking, well, what good is this? What can you use this kind of thing for? Well as getting that, we did another little experiment to demonstrate what the value of this was and what you could use it for. I remember I said we had 5 corner reflectors sitting on concrete posts. Well, the one in the middle, we were able to move it between passes. So I don't know if you can see it, but there's a micrometer-driven stage here, so that between each pass, I would radio down to a student working for me and say, okay, we finished pass 2, you can move the corner reflector. And he would adjust the micrometer here, and of course that's an accuracy of, fraction of a millimeter. And then we would fly it again, and we did it 8 times, and I told him to take the page from his notebook, tear it out, put it in an envelope, seal the envelope, and give it to our director. I didn't want to know how the movement had been done. And then afterwards, he went back to Waterloo. He was a student there. Afterwards, we processed the data, discovered that yes, indeed, we did have what's called coherence, and we were able to solve for the movement of the corner reflector. And for combinations of pass 4 and 6, 6 and 8, and 4 and 8. And these are the solutions, and this is what the student had said. So the mean error was a little more than 1 millimeter. So this was, in a sense, the point of the whole exercise. Can you see relative movement within a scene at a fraction of the wavelength? So this didn't lead to a lot of work with aircraft, but it certainly did with satellites. So now it's a relatively large field where the radar satellites are in what called repeat orbits. So with RadarSat, it images the same part of the Earth every 24 days. And that's within a few hundred meters. The satellite's within a few hundred meters, so that you satisfy the conditions for interferometry. And as long as the terrain has not changed much in the meantime, in that 24 days, you can see things like a volcano inflation, deflation. You can see, if you're lucky enough to have an image before and after an earthquake, you can see the way the Earth moves. If you've got extracting oil or water or mining, you can see the way the surface of the Earth has moved. We showed that you could measure the way glacial ice moves. So this is now a big field. It's called repeat track interferometry, and it's and NASA's even proposed a satellite radar system where the primary function would be this kind of work. And in a sense, we did it first with our aircraft. In fact, it's harder to do with an aircraft than it is with a satellite, because with the satellite, you don't have the motion compensation problem. As you all know, aircraft do not go through the sky in a nice straight line. And we had to do this motion compensation effect. Okay, well, having done that, we can also do some more with this principle, the principle of deriving the very small line of sight difference in range. So now we can put the extra antenna on the side of the aircraft. So with what's called a cross-track interferometry, we transmit from this antenna and receive from both. And now you've got a stereo effect. You know the range very accurately, the difference in range very accurately, so you can derive elevation. And this simulation here was based purely on the radar data, nothing else, no digital elevation model, just the radar data. So we derive the elevation from the stereo radar data. We can create a map-like product, and therefore you can do any kind of fly-through or simulation. The other thing we can do is, this antenna is a phased array receive-only antenna, but we can split it into two. We can split it into a forward antenna and an aft antenna. In other words, those two antennas view the scene at a slightly different time. So if something is moving towards or away from the aircraft, there will be a phase shift. And you can measure that, and therefore you can derive a target motion. And I'm sorry, I don't think you can see this very clearly, but this is Bay of Fundy. This is Cape Split, and what we've done is flown twice. So the two flight lines are orthogonal to one another, so that we can get two components of the radial motion and derive the current surface currents around Cape Split as Cape Split. And whenever the program was shut down and the plane went to environment, the scientists at Defense Research continued doing some work with this mode. In fact, they used this again to demonstrate what they might be able to do with RadarSat. And there is a moving target mode on the RadarSat 2 satellite. And of course, the military is interested in this approach as well. Let's see. Okay, so that's my little description of some of the science that we did in the data acquisition division of C-GRSC. That's only a small part of it. There was work done in geology. Whoops. What happened? Back up. Many fields, and I think it is true to say that without the success of the airborne program, we wouldn't have the successful radar program, satellite radar program that we have. RadarSat-1 lasted for 18 years. They hoped to get 5 years out of it, they got 18. RadarSat-2 is up there right now. It was launched in 2005, and it's continuing to work very well. I think it's the best civilian radar in orbit at the moment. So thank you very much. I'm sorry we've all gone a little long in time. We'll give us a